Why, hello. Today we're going to go on to section 16.4, which deals with double integrals in polar coordinates. Now let me preface this before we even get started. A lot of times students, when they took Calculus 2, had trouble with polar coordinates, and therefore they decide that if at all possible, I will never use polar coordinates to do an integration problem. We use polar coordinates when the region that we want to integrate, that the one that's on the xy axis, your basis, is circular in nature. If we have something here, this is just a circle of the center is the origin and its radius of 1. So what you have is your r. If you take any arbitrary point in this region, r theta, your r is between 0 and 1, and then of course your theta is between 0 and 2 pi. If you have a region that looks anything like this, you could have an annulus where you have your radius ranging from, if you take an arbitrary theta coming along here, your r could range from 1 to 2 in this case, and then we could think about what does our theta range from. Well, if we go all the way around the circle, your theta is going to be going from 0 to 2 pi. You're going to find if you have a region that's circular in nature, if you take the time to change your integration, change your x coordinates, change your y coordinates, change your limits of integration into polar coordinates, you will find that the integration is a whole lot easier to do than it would be using x's and y's. So for that matter, for this particular region deals with taking an integral that's in xy rectangular form and changing it to polar coordinates. So first of all, we have to review what are polar coordinates. And we're not going to be doing anything real difficult in this section, even though the integrations sometimes get a little bit hairy, because we assume that we remember everything from Calculus 2 in Chapter 8 when we did every which way to integrate. So we'll have to review some of those topics. But first of all, if you take a point and it has polar coordinates r and theta, we should all remember that r is the distance that the point was from the origin. In xy form, you go over x up y. So in this right triangle, if this is x, this is y, this is r. Since opposite over hypotenuse gives me the sine of the angle, if I multiply through by r, I'll get y is equal to r sine theta. Since adjacent over hypotenuse is the cosine of the angle, and you multiply through by r, you would get x equals r times cosine theta. And so we have this identity and this identity, which are all right here. And these are going to be the cornerstone of what we're doing today. Okay? So in summary, oh, no, not in summary. First of all, we're going to have regions that are going to be circular in nature. But what's going to happen when we do those regions, we're going to have little radii emanating from the origin. And then we're going to ask, as we take increments of r, we want to represent that little area, which we call delta A. And the question is how, if I have these little radii emanating from the origin, and then looking at your little delta r's, so you can even have all of these coming in like that, we're going to be looking at any one of these little regions and saying what delta A is. Before, we had little regions that looked like this, and it was quite obvious that if you had delta A, it was just delta x times delta y. Now the question is, in this chapter, how can I represent that little delta A? Your book does a very nice job of developing it formally. We're going to do it informally because we have a lot to do today. And I just want you to recall, this is really from an Algebra Trig 1 kind of problem. If you had a circle, all right, and you were only interested, you had a little, I call it delta theta, a little angle right here, and if I wanted to represent this arc length, if you might remember back from your Algebra Trig days, your arc length is equal to your angle times the radius of the circle. Okay, and in particular, if I let my delta theta be all the way around the circle, if I went all the way around the circle, I would get the circumference of the circle. The angle all the way around the circle would be 2 pi, and the circumference of a circle is 2 pi r. But if I just want part of the circle, and I just have a small radius, I mean not a small radius, but a small angle, my arc length, that a lot of times we use as s, is equal to the angle times the radius, or it might be better to write it as r times delta theta, okay? Or back in Trig 1, we just wrote it as s is equal to r times theta. I chose it delta theta because my theta is going to be small in this instance. So using that, if I wanted to represent this little area right here, just to help you remember why we do what we do, if I look at, this is my radius, and this is my delta theta right here, this arc length right here is equal to r times delta theta. And from here to here is how much we're increasing r. Well, if delta r and delta theta are small, relatively small, this little region right here looks very much like a rectangle. And if we take length times width, we can say our delta A is equal to approximately r times delta theta times delta r for our area here. And so therefore, if delta theta and delta r are very small, instead of writing it as delta A, we could write it as dA is equal to r times dr d theta. So in other words, if we wanted to do an integration, and we have some integral over some region r of f of xy dA, in rectangular coordinates, we always wrote dA as dx dy or dy dx, depending on how it would be easier to do the integration. Now, if we want to do it in polar form, what we need to do is replace x with r cosine theta, replace r with r sine theta, and replace dx dy with r dr d theta. All right, so today what we're going to be doing for the next hour, or maybe a little bit more than that, depending on how complicated these are, if I have an integration that's in terms of x's and y's, and I want to change it into polar form, what I need to do is wherever I see x, I replace it with r cosine theta. Wherever I see y, I replace it with r sine theta. And whether I had dx dy or I had dy dx, I replace that with r dr d theta. And that is how we're going to do our integration using polar coordinates. Okay? The first one I want to look at is an example from your textbook. And they want me to evaluate over the region R the function 3x plus 4y squared dA, where R is the region in the upper half plane bounded by the circles x squared plus y squared equals 1, and x squared plus y squared is equal to 4. All right, now first of all, notice here, let's draw our region. Let's see what our region looks like. All right, the circle x squared plus y squared equals 1 is a circle of radius 1. Okay, radius is 1. X squared plus y squared equals 4. That's x squared plus y squared equals r squared. So your r squared's 4 in that case, or your r is 2. So that's a circle of radius 2. Okay, and we want to find our region is, now it says where r is the region in the upper half plane, right, bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. All right, now when it says upper half plane, I'm going to assume that they're talking about being in the half plane above the x-axis. Okay. All right, now I want to change, now I have my region, I want to change this integration into polar form. So wherever I see x, I replace it with r cosine theta. Wherever I see y, I change it with r sine theta. Okay. So here's my integration. I have the integral, double integral of 3. Wherever I see x, I put r cosine theta. Wherever I see y, I put r sine theta. So that's going to be squared. And for dA, I can put r dr d theta or r d theta dr, whichever it's easier to do the integration. Usually students try the dr d theta first, and if that doesn't work, they'll try d theta dr. Now we have to figure out our limits of integration. Now, just like when we did it with the xy plane, I said if you integrate with respect to r first, you have to pick an arbitrary theta, move along that theta, and ask what is r changing from. Okay? So I pick an arbitrary angle theta in the region. There's an arbitrary theta. As I move along that theta in the region, notice I'm going from here to here. What is r changing from? R is changing from 1 to 2. Now, now I have that arbitrary theta, but what does my theta have to range from to get the entire region? Well, my theta is going to have to start here, and then we're going to go all the way around until we end up here. So we're going to go from 0 to pi. Okay? Now we have to do the inner integral first. So I think I'll get a fresh sheet of paper for that. And we have to do, what is the integral? Because we're going to do this inner guy first. Okay, so I'm going to do, what's the integral from 1 to 2 of, and let's see, it's going to be 3. Notice you have 3r cosine theta plus 4r sine theta squared times r. So it's 3r squared cosine theta plus 4. You're going to have r squared times r is r cubed sine squared theta dr. All right. Now in this particular one, this is pretty easy. Remember, r is changing. Theta is just a constant. So this inner integral is real easy. It's r cubed. Bring cosine theta along for the ride because cosine theta is a constant. Because if we're integrating with respect to r, your theta is constant. The second piece, theta is a constant. So the integral of 4r cubed is just r to the 4th. And bring sine squared theta along for the ride. And we're integrating from r equals 1 to r equals 2. Plugging that in, I get 2 cubed is 8 cosine theta, plus 2 to the 4th is 16 sine squared theta, minus, plugging in 1, I get cosine theta, plus sine squared theta. And combining similar terms, 8 cosine theta minus cosine theta is 7 cosine theta. And 16 sine squared minus sine squared is 15 sine squared theta. Okay, we're doing all right? So that's my inner integral. All right, now I'm ready to take that and plug it in to this integral right here. So this is the integral from 0 to pi of 7 cosine theta plus 15 sine squared theta d theta, as theta ranges from 0 to 2 pi. Now, no one's going to have trouble doing this first integral, but I think a number of us are going to have trouble doing this second integral, the 15 sine squared theta. So shall we talk about that? How do I do that integration? How do I integrate if you have cosines? Because this is going to come up over and over again in this section. Because we're changing everything into polar form, you're going to end up getting integrals that have cosine squareds and sine squareds. Let's review. Back from our chapter, Every Which Way to Integrate. How do you integrate a cosine squared or a sine squared? In fact, how do you integrate cosine to an even power or sine to an even power? How do we do that? We use the substitution. If you have cosine, you replace cosine squared with 1 plus cosine 2 theta over 2. And if you have sine squared, you replace it with 1 minus cosine 2 theta over 2. You might want to put that on your cheat sheet if you forget. But if you have cosine squared or sine squared, you make this substitution. Okay? We're going to have, I think, 3 problems today that are going to be using this substitution. So it's going to come up. And it's not going to go away because in the last section I do in this chapter with cylindrical coordinates, guess what? We're using r and thetas all over again. Okay, so using that, coming back here, I have here this is equal to, now this is going to be the, I'm going to write this as 7 integral from 0 to pi of cosine theta, d theta, plus 15 integral from 0 to pi of sine squared theta d theta. Okay. And bringing that along for the ride, this one is going to be 7. The integral of cosine is sine. And we're going from 0 to pi. Plus 15 integral from 0 to pi. For sine squared, I replace it with 1 minus cosine 2 theta over 2 d theta. Okay. And this one, if I plug in pi, I get 7 sine pi minus 7 sine 0, plus, and this one I'm not ready to do the integration yet. Well, why don't we bring out the halves, so we can write it as 15 halves integral from 0 to pi of 1 minus cosine 2 theta. This one I can do right now, because what's the sine of pi? What's the sine of pi? 0. Think of what sine looks like. It looks like this. At pi, it's at 0. So this is 0, that's 0, so that's just a big goose egg. Plus 15 halves times, now, to do this integration, what's the integral of 1 d theta? Theta. Okay. And what is the integral of cosine 2 theta? It's going to be sine 2 theta, but you'll need over 2. And to check yourself, the derivative of this should give me what's inside. And when I take the derivative of sine 2 theta, I get cosine 2 theta times 2, and the 2's cancel. If you're not comfortable with that, you know, you're going to do, if you're not comfortable with that, in figuring out the integral of cosine 2 theta d theta, you need to go through with a u substitution of u is 2 theta, so du is 2 d theta. So you can say I need a 2 here and a 1/2 here. So this is 1/2 integral of cosine u du, which is equal to 1/2 sine u, which is 1/2 sine. What's my u? It's 2 theta. All right, and then we're plugging in from 0 to pi, which gives us 15 halves times pi minus sine 2 pi all over 2 minus 0 minus sine of 0 over 2. Sine of 2 pi is 0, sine of 0 is 0, so we just have pi times 15 over 2, which is 15 pi over 2. Very nice problem. The one thing I sort of cringed when I decided what we were going to go over is I thought, oh, I know for sure they're going to forget to do this when you have a trigonometric substitution to do. You use this whenever you have sine or cosine to an even power. So if you had cosine to the 4th or cosine to the 6th, heaven forbid, you would use this. Okay? All right, let's go on to the next one. It says, evaluate the integral by changing to polar coordinates, where r is the region that lies in the left of the y-axis, lies to the left of the y-axis, between the circles x squared plus y squared equals 1, and x squared plus y squared equals 4. Well, first of all, I'm going to draw my region right here. X squared plus y squared, everybody should know, x squared plus y squared equals r squared is a circle of radius r. So this first one is a circle of radius 1. We have a radius of just 1 here. And the second, again, yeah, Mrs. Strocko, is a circle of radius 2. Except they're limiting me on my region here. They're telling me I'm going to have a region that lies to the left of the y-axis. So they're just talking about this region. This is called an annulus. You'd be a fool to do this in any other way than with polar coordinates. So now I have to change my whole integration into r's and thetas. So I have integral. Where I see x, I replace it with r cosine theta. Where I see y, I replace it with r sine theta. And where I see dA, I replace it with, don't be telling me dr d theta. If you do that, you're going to bomb the test. It's r dr d theta. Okay, now I have to figure out my limits of integration. All right, I'm going to look at my region here. If I'm integrating with respect to r first, tell yourself, pick a line of arbitrary theta. Arbitrary theta is like, I think of it as a spoke on a bicycle. It's going to be coming out like that. That's an arbitrary theta. You can see all your spokes, you're going to go from theta equals this to theta equals this. Here's an arbitrary theta. What is r ranging from? Piece of cake. From 1 to 2. And what does theta range from? Well, I go from theta equals, theta up here is pi over 2 to theta equals 3 pi over 2. Okay. All right, going through this one's a fairly easy one to do. Doing this integration, first we're going to do the inner integral. So I have to figure out what is the integral from 1 to 2 of r cosine theta. Why don't we write it as r squared? Students always forget to multiply that through. It's going to be r squared cosine theta plus r squared sine theta dr. And in fact, notice, what I'm going to do is I'm going to factor out cosine theta plus sine theta. Because I can think of this as one big old constant times r squared. So when I do my integration, bring my constant cosine theta plus sine theta along for the ride, and that's going to be r cubed over 3. Is that okay if I do it that way? And we're going from r equals 1 to r equals 2. So if I plot, so I really just have this constant cosine theta plus sine theta over 3 times plugging in 2, 2 cubed is 8, plugging in 1, 1 cubed is 1. So that's a big old fat 7. So I just have 7/3 times cosine theta plus sine theta, which isn't bad. We all okay? So I'm going to take that and plug it into here for my inner integral. So I'm going to go from the integral from pi over 2 to 3 pi over 2 of, pop the 7/3 out front, cosine theta plus sine theta d theta. You guys know how to do that integral. We're not going to waste time. We have too many things that you don't know how to do that we got to talk about today. You're going to go 7/3. What's the antiderivative of cosine? Sine. And by the way, people, you are allowed to use the front flap, back flap of your book. So if you get confused whether the integral of cosine is plus or minus sine, look it up. I don't want you losing points. So that I get sine, and this is going to be minus cosine. And we're going to go from theta equals pi over 2 to theta equals 3 pi over 2. Pop in the 3 pi over 2, blah, 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 minus pop in the pi over 2. Follow along, and you're going to end up with minus 14/3 for the answer. You can leave that in a little blank, and you can fill that in yourself. Okay? All right, let's look at this one. They want us to evaluate the integral over the region R of square root of 4 minus x squared minus y squared dA, where R is the region of the points x, y, where x squared plus y squared is less than or equal to 4, and x is greater than or equal to 0. I think what I want to do first of all is just draw the region. What does x squared plus y squared less than or equal to 4 look like? It's a circle. Circle of radius 2. I draw the saddest circles. I apologize. It's a little lopsided, but use your imagination. And we're talking about everything inside the circle, right? Because if your radius is less than or equal to, r squared is less than or equal to 4, so r is less than or equal to 2. We want everything inside. But then they say, no, 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 no. X has to be greater than or equal to 0. So we want just this half. Okay? Now, we're ready to do our integration. Does everybody, we'll look at that in a second when I do my limits of integration. Okay, but coming in here, do we all notice I can write minus x squared minus y squared as minus quantity x squared plus y squared dA. All right? And therefore, people, this would be the double integral of square root of x squared plus y squared is r squared, and dA is r dr d theta. Now let me talk about the kinds of problems I see when I'm grading tests. Maybe if we talk about it, maybe we won't make those mistakes. Okay? What I see, a big no-no that I see students do, they look at this and they say, okay, Ms. Strocko, I'm integrating with respect to r. No problem there. Pick my arbitrary ray. What's r ranging from? It's ranging from 0 to 2. Then they say, oh, okay, well, what's my theta ranging from? And they say, well, my theta could be here, and then I can go all the way up to here. And so my theta is ranging from, and what they'll tell me is, theta down here is 3 pi over 2, and theta up here is pi over 2. And I can guarantee you, if you do that, you're going to get a negative answer. Why is that wrong? What's wrong? Let me show you what's wrong. When you do your limits of integration, you're saying this is your lower bound, and this is my upper bound. So you're saying theta is 3 pi over 2 here, and I'm adding up all these angles. Well, if theta is 3 pi over 2, and I'm rotating this way, What's theta here? No, 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 no. If I'm rotating this way and I look at my angle's increasing, right, when I'm going this way, it's 2 pi, right? Because you're 3 pi over 2, you're increasing, you're going to 2 pi, and then the appropriate angle up here would be 5 pi over 2. If you think about it, if you made a little number line here and you said here's theta, if you're at 3 pi over 2 and you're increasing that angle, you're never going to get to pi over 2. Pi over 2 is over here. You're past it. You with me? So in respects, if you're going from 3 pi over 2 to pi over 2, you're going backwards. So instead, if you want this to be pi over 2 and you want this to be 0, if I rotate this way to find out what this angle is here, what does that angle have to be? Aha! Minus pi over 2. Because if I increase minus pi over 2 and I'm going this way, I'm going to get to 0, and then I'm going to get to pi over 2. Look at the number line. Think of this as if this is your theta number line. Here's 0. You're going to go minus pi over 2 to 0 to pi over 2. Yes, so this limit of integration right here is going to be minus pi over 2 to pi over 2. The easiest way to remember it is this. If you're going to go from here to here to name these angles, it's a continuum. This is pi over 2. This is 0. If I'm rotating this way, I'm going to be doing negative angles. That's a minus pi over 2. This integral is very easy to do because look how lovely this is. This one is one when you go, wow, I love polars. There's going to. You could have, yeah. That would have been okay. Yes, yeah. If you had made this be 3 pi over 2, 5 pi over 2, and you as an exercise might want to do that, or do it on your TI 92 or your 89, or do it on Maple, but we don't have time to do it 5 different ways. So I'm going to take my inner integral, and look how nice this one is. And I'm going to work hard to make your test have ones that are this nice. You have 4 minus r squared r dr for your inner integral. How am I going to do that integration? U substitution. U is 4 minus r squared. And so therefore du is minus 2r dr. So if you want, you could say minus a half du is r dr, if you like to do it that way. So this becomes integral from 0 to 2 of u to the 1/2, and r dr is getting replaced with minus 1/2 du, which is minus 1/2, increase your exponent by 1. Dividing by 3/2 is the same as multiplying by 2/3. So it looks like I have minus 1/3. What's u? It's 4 minus r squared. Don't forget the 3/2. And then we're having r ranging from r equals 0 to r equals 2, which gives me, if you have a constant, just factor them out. Oh, excuse me, that's no 0 there. That's a what? 2. Pop a 2 in here. 4 minus 2 squared is 0. 0 to anything is 0. Minus, putting a 0 in here, we have 4 to the 3/2, but we all can figure out 4 to the 3/2, because the half power says take the square root because you have 2. Cubic gives you 8. So we have minus a third times minus 8, which is going to give me 8/3. Now, just because I got a number, don't think you're done. That was the inner integral. Okay, so, but God is good, because if the inner integral is 8/3, this whole mess here is just 8/3. We can pop the 8/3 out front. So I just have a little 1 there, and the integral of 1 d theta is theta, and we're going from minus pi over 2 to pi over 2, which is 8/3. Pop in the pi over 2, minus, pop in the minus pi over 2. And pi over 2 minus pi over 2 is plus pi over 2, which gives me pi times 8/3. Nice problem. That one was sort of fun. I wish they all would be fun, but that one is especially nice. I like that one. Any questions? Nope? Okay, let's look at this one. This one, let's draw the region first. The region is the first quadrant bounded by the semicircle, x squared plus y squared equals 25. I don't know why they say bounded by the semicircle. It should be saying bounded by the circle, because x squared plus y squared equals 25 is the circle of radius 5. This is a 5. All the way around it's 5. But it says it's in the first quadrant. So we're just talking about, this is our region D. Okay, ready to go. Huge part of the credit on these problems is changing your integration into r's and thetas. So it's the double integral. Where I see y, I put r sine theta. Where I see x, I put in r cosine theta. Where I see dA, I put r dr d theta. Okay? Next thing is, what's my limits of integration? If the limits aren't easy, go back to rectangular form. But this is going to be very nice in terms of limits. Take an arbitrary theta in the region. What is theta ranging from? 0 to 5. And if I take all my thetas, they're going from 0 to pi over 2. Okay, so now we have to do the inner integral. This one's going to give us a little bit more of run for our money. Okay, the inner integral is integral from 0 to 5 of, I'm going to write this as e to the r cosine theta times r squared sine theta dr. Okay, if I got that right. Okay, I have r sine theta, e to the r cosine theta, and r dr d theta. Now notice with this particular one, if we're integrating with respect to r, you could think of sine theta as a constant, so you can throw this out front. Okay? But how am I going to do that integral? E to the, because the cosine theta is acting like a 5. So if you want, if you're struggling on how you're going to do this, you could say this is e to the 5r, r squared dr. You follow? Because cosine theta is acting like a constant. How do you do that integration? Pardon?
Integration by parts?
Yes. Integration by parts. Unfortunately, people, it's going to be integration by parts twice. It's going to be integration by parts twice. Because you're going to let your u be r squared. du is going to get knocked down to 2r dr. You're still going to have an r e to the r. You're going to be doing parts twice. Okay? I don't want to do parts twice. I only want to do parts once. So we can always go back. Notice, with this particular integration, the limits of integration were constants. If the limits of integration were constants, just like when we did the rectangular, you could switch the order. We could also switch the order in terms of r and theta. So let me go back and look at how could I switch. I mean, we could, you as an assignment can go do this, but I'm going to show you a good mathematician's a lazy mathematician. I'm going to go back and look at my integration. And I had r sine theta times e to the r cosine theta times r. I'm going to look at d theta dr. Oops, d theta dr. Be nice if I had whiteout or an eraser. Now, if I integrate with respect to theta first, what's theta ranging from? From 0 to pi over 2. And then what's r ranging from? From 0 to 5. You can only do this when your limits of integration are constants. You know, if you had r ranging from something to something in terms of theta, you could not flip-flop that order. Okay, so I'm going to get rid of this guy. I'm going to keep this guy, though. All right, and now, let's do this inner integral. I have the integral from 0 to pi over 2 of e to the r cosine theta times r squared sine theta d theta. Okay. R is a constant, so we could throw the r squared out front. What do you think, people? How can I do this? U could equal r cosine theta, absolutely. So we're going to let u equal r cosine theta. So what does du equal? Derivative of cosine is minus sine d theta. Okay, so if I change this to u's, I have the integral. Now let's see. I think, yeah, I'll go minus, that doesn't look like a minus, but minus 1 over r du is equal to sine theta d theta. So this gives me r squared integral from 0 to pi over 2 of e to the u. And for sine theta d theta, I'm going to replace it with minus 1 over r d theta. Okay, everybody doing okay? And if we could bring this constant out front, which gives me minus r. We have the integral from 0 to pi over 2. Oh, this was a du, excuse me. E to the u du, which is e to the u. And what's u? U was r cosine theta. And we're going from theta equals 0 to theta equals pi over 2, which is going to give us minus r times e to the r cosine pi. I need another piece of paper. This is equal to minus r times e to the r cosine pi over 2 minus e to the r cosine 0. What's cosine pi over 2? 0. E to the 0 is 1. What's cosine of 0? 1. Think of what the cosine graph looks like, right? Cosine graph starts up here, right? Like that. So it's going to be e to the r times 1, which is e to the r. So we could write this as minus r plus r e to the r. Unfortunately, that's just the inner integral. Minus r times 1 is minus r times minus is plus r e to the r. But at least we didn't have to do parts. But now we do. Because we have to take this, and plug this in for this guy. So now I have the integral from 0 to 5 of minus r plus r e to the r dr. All right. I prefer to break this up into two integrals. Because that one I can do in a second. That one's going to be minus 1/2 r squared. We're going from 0 to 5. Factor out the minus 1/2. Pop in the 25. Minus pop in the 0. And he's done. This guy is going to take a little bit of work. Okay? Now, I will be honest with you. In the homework, I strongly suggest that you do as many integrations as you can. You want to do one with parts. You want to do one with this trig substitution, because you do get points on your test in terms of whether you know how to do integration. Part of Calc 3 is reviewing Calc 2. But it can get extremely tedious. Setting up the integrations is really the most important thing. Making your substitution for x and y is the most important thing. Knowing that dA is replaced with r dr d theta is the most important. So if you're here at Del Tech, or even if you're down UD, you can use Maple to do your integrations. You know, half of them do the integrations all the way out, but some of them, if you don't have time to go through and do all of them, you can take up at 92 or an 89 or your Maple to check to see if you do get the way you set it up, if it's going to give you the answer that you're going to get. Talked long enough. How are we going to do the integral of r e to the r dr? If you don't like r's, make them x's. How do we do that? Parts. Integration by parts. Okay, how does integration by parts do? Integration by parts says the integral of u dv is equal to u times v minus the integral of v du. We have to ask what's u and what's dv, because that entire integration, in fact, we're going from 0 to 5. I can bring that along for the ride. That entire integrand has to be used up in terms of u and dv. We check what u is. We pick u is by Lipitz. I don't have a logarithm there. I don't have an inverse trig. I do have a polynomial. Polynomial is just an x or an x squared or an r, if that's the variable that we're using. And so my dv is e to the r dr. So du is dr, and v is the integral of e to the r dr, which is e to the r. So this integral is going to equal, this one right here, is going to equal u times v, so it's r e to the r minus the integral of v dr. This is a fair one, because it's a fairly simple integration by parts. It's not too horrendous. And we're going from 0 to 5, 0 to 5. So down here we put in 5, minus, you put in 0, you get 0. Minus, what's this integral? E to the r dr is e to the r, and we're going from 0 to 5. So it looks like I have 5e to the 5th minus e to the 5th minus e to the 0, right? Which gives me 5e to the 5th minus e to the 5th, and minus a minus is plus, e to the 0 is 1. So it looks like I have 4e to the 5th plus 1. Okay, everybody with me? All right. And let me go back and look. What was the answer that we should get? Ooh, the answer says it should be 4e to the 5th minus 23 halves. So we might want to go back and see where I messed up. Shall we go back and look?
You have to add from the other one.
Aha! Let's go back. Thank you very much. Going back. Where's my up? There we go. It's right here. We have 4e to the 5th plus 1 for this integral. Thank you very much. So remember we had the two parts here, and we said we have to do this and this. We just spent this entire page just doing that one little piece, which turned out to be his. So we have plus 4e to the 5th plus 1, which is going to give us minus 25 halves plus 4e to the 5th plus 1, which I'll write as 2 halves, which is 4e to the 5th minus 23 halves. Complicated problem, but thank goodness we got it correct. Okay. On your test, people, it takes me about 40 minutes for each student to look at because I go through all your work because there's all kinds of pitfalls. All right, let's look at the next one. The next one, I like this one. This one is important that we need to look at. We're looking at the integral of x dA, where D is the region in the first quadrant that lies between the circles x squared plus y squared equals 4 and x squared plus y squared equals 2x. This one's going to give us a run for our money. Okay, so let's go and talk about it, what it looks like. There's multiple ways that we could do this. I prefer to just use polar coordinates. Okay, so let's change these two equations to polar coordinates. I'm using the fact that x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So this one, I can see what it looks like. It's a piece of cake. It's a circle of radius 2, 1, 2, 1, 2. That's the first guy. Second guy, does anybody know what that looks like? Okay, let's change it into polar form, okay? X squared plus y squared is r squared. X is 2r cosine theta. You can divide by r on both sides. So that gives you r equals 2 cosine theta. You might not remember what r equals 2 cosine theta looks like. You have no problem. You can pick up your calculator. Now, if you have a TI-92, that's fine. The TI-92 acts no differently than the TI-83 in terms of graphing things in polar. So let's turn it on. I'm going to hit my mode button. And I come down here. And if you have a TI-83, you're going to hit the mode also. I want to be in what form? Polar, which is option 3. Okay. I'm going to go to second y. Oh, I better hit enter first. Then I'm going to go second y equals, or y equals. Whoops, I thought I had it in polar form. It's not in polar. Let's go back. I want option number 3 is polar. Hit 3. Hit enter. There you go. Now I have r equals. I'm going to come down here and turn that guy off, clear. The function I want to look like as r equals 2 cosine theta. Now think, r is how far you are from the origin. Cosine can't get any bigger than 1. So your r can't get any bigger than 2. So your x can't be bigger than 2 or negative 2. Y can't be bigger than positive 2 or negative 2. You see why? Because r is how far you are from the origin, right? So I'm going to type in 2 cosine, and I have a theta button, which is nice. And you also have a theta button on the 83. Hit enter. I didn't notice on my mode. Am I in radian mode? Yes, good. That's fine. Because it'd be embarrassing if I didn't have it in radian mode. Now I'm going to go second window. All right, and I want it to go from 0 to 2 pi. That looks fine for my t-step. But my x min is going to be negative 2 to 2 because the farthest you are from the origin is 2. And I'm going to make my y min negative 2 to 2. And this is fine. I could say, oh, everybody should know what the graph looks like in polar. But I have found most of my students do not. And then I'm going to tell it to graph it. And look what I get. Whoops. I shouldn't be getting that. So let me go back and see what I have in here. Well, let me go back and look at what I typed in. My vision's not so. Oh, did I have something else in there?
Yeah, R1 is you had R is equal to 1.
Oh, let's go back up. Yeah, my vision's not so good. Second y equals. I know what it's supposed to look like. It's still graphing. Second y. I have to wait till it finishes. There, okay, there. Second y equals. Oh my goodness, I did have a 1 there. I apologize. That was drawing me a circle of radius 1. I just want to have clear. I want 2 cosine theta. I apologize. And I don't want it twice, so let's clear that guy. All right, now let's tell it to graph it. It should be a circle that's hugging the x-axis. The way I remember it is, it's hugging the x-axis, cosine goes with the x-axis, and the furthest point is 2 units away. That doesn't look like it's a circle, but if I go to zoom, zoom is F2. If I hit F2, and I come down here to z square, which is option 5, and hit enter. As you can see, it's squaring it up. It's making your units in the x direction and in the y direction equidistant. You're getting a circle that's of radius 1. It's a circle of radius 1, centered at 1, 0. If you hit trace here, trace is option F3. There's the point x, 2, 0. Okay, so that's enough. Coming back here, this is a circle that's right here. Okay, now I could have said another way you could have done this. You know, I just think it's nice to mention these things to students. Another way you could have done this is when you had x squared plus y squared equals 2x, I could have said, duh, do this. Get equals 0 plus y squared equals 0. Let's complete the square. Divide that by 2 gives me 1. Square it gives me 1. I'm going to add a 1 on both sides. Complete the square. This is x minus 1 squared plus y minus 0 squared equals 1. It's a circle whose center is 1, 0, and whose radius is 1, square root of 1, which is 1. Okay? All right. So this right here is r equals 2 cosine theta, and this one is r equals 2. Now, they want me, let's read what it says for the region. I got my 2 borders. D is the region in the first quadrant, so we're just in the first quadrant, that lies between the circles. We're talking about this region right here. Okay? Again, it's no problem if you have something in polar form to put it in the calculator to visualize what it looks like. Now playing plug in. Where I see x, I put r cosine theta. Where I see a, normally we go dr d theta. Unless it's uncomfortable, then we might try d theta dr. Now we have to look at our picture. Since I'm integrating with respect to r first, pick an arbitrary theta in the region. And what is r ranging from? If you go along here, you're not in the region. You're in the region right here. What is r equal to here? 2 cosine theta. And as I increase my r on the outer rim, what does r equal? 2. And if I add up all these thetas, thetas ranging from 0 to pi over 2. All right. We're going to do the inner integral first, or at least talk about it. I don't know if I'm going to go through and do all these integrations. I'm getting a little tired, so you probably really are getting tired. Question? Any questions on anything I wrote so far? Anybody having problems with that limits of integration that I just did? Because I can do it again.
I don't understand why it goes from 2 cosine pi to 2.
Okay, take an arbitrary ray of an arbitrary angle theta emanating from the origin. As I move along that arbitrary theta, am I in the region right now? No. Am I in the region now? No. I am in the region right here. At that point, what is r? It's this inner circle whose equation is r equals 2 cosine theta. So right here, r is 2 cosine theta, and as I increase r in the region, at the very next border, r is equal to 2. So you're going from inner inner border to outer border. So that's why you're going from 2, because we're saying r is ranging from 2 cosine theta to 2. If you fix theta. And what you're doing is you're going to do all these arbitrary thetas, and then you're going to sum them up. And that's what that guy's going to do. Okay, now this one, the inner integral is pretty easy, so we can zip through that quite quickly. We get r squared cosine theta dr from 2 cosine theta to r equals 2. In here, r is what's varying. Cosine theta is a constant, so you're going to get 1/3 r cubed cosine theta. Okay, I don't know if I'm going to go through this entire one. I just want to mention some things. We're going from r equals 2 cosine theta to r equals 2. So if we factor out our 1/3, you put in r equals 2, you get 2 cubed, which is 8 cosine theta, minus, you pop in a 2 here, you're going to get 2 cosine theta cubed times cosine theta. Everybody with me? So I have 1/3 times 8 is 8/3 cosine theta minus 2 cubed is 8, so it's 8/3. And then you have cosine cubed times cosine, which is cosine to the 4th. All right? I want to have time to look at other things, so I'm just going to comment what we need to do to finish this integral, to do the outer guy. The outer guy is going to be the integral from 0 to pi over 2, 8/3 cosine theta minus 8/3 cosine to the 4th theta d theta. Okay, that's the outer guy. Now, we're not going to go through the whole thing, but I want you to finish this. Take this one, piece of cake. You guys know how to do him. He's not a problem. We don't need to talk about him. This guy we need to talk about. How do we integrate a cosine to the 4th? We go back and we use this. Cosine squared theta we replace with 1 plus cosine 2 theta over 2. So if you have cosine to the 4th theta, think of that as cosine squared squared. So you're going to replace cosine to the 4th with cosine squared, and cosine squared you're going to replace with 1 plus cosine 2 theta over 2. Okay, now what's squared? Now what happens is when I replace, so I think of cosine to the 4th, this is just ditto, bring down here, don't worry about it. With this baby cakes, and you're going from 0 to pi over 2, you're thinking of cosine to the 4th as cosine squared squared. So you're going to replace that with 1 minus cosine 2 theta over 2 d theta and squared. When you do that, the 1/2 squared is a quarter. I can throw him out front. But inside here, when I go 1 minus cosine 2 theta squared, I'm going to get 1 minus 2 cosine 2 theta plus cosine squared 2 theta. You with me? How am I going to do that integration? Yes, 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 yes. You're going to have to do it again. It's a little bit bloody. You're going to have to look at the cosine, this guy right here, cosine squared 2 theta, and you'll say to yourself, wait a minute, Mrs. Strocko, I know cosine squared theta is 1 plus cosine 2 theta over 2. If you have cosine squared of an angle, all you have to do in this formula is double the angle. So you would replace it with 1 plus cosine, yes? Oh, this should be plus, I apologize. Because cosine is a plus, that's a plus, thank you very much. I'm talking about big picture and forgetting a minus sign. So if I have cosine squared 2 theta, it's going to be 1 plus cosine double that angle over 2. And that's what's going in here. Okay, so the point is this. Whenever you have cosine of an even power, you use this substitution. And if you go through and do it, and in fact I can post this written out on the web if you'd like, or even it is written out. Now I'll post it on the web. Your answer is going to be 8/3 minus pi over 2. Okay. Okay, let's look at setting up a few more. We did this one. Oh, this one's very important, and it's not too hard, so we need to talk about it. Use double integrals to find the area enclosed by one loop of r equals cosine 2 theta. First of all, most of you might not even remember what that looks like. So if we come back and I go to y equals, and fortunately I'm in polars right now, the function that I want to look at is cosine 2 theta. So I'll come up here, I bring it down, I hit clear, and I'm going to put in cosine of 2 theta. Oops, yeah, hit enter. There you go. An appropriate window, 0 to 2 pi would be fine. My x's and y y's have to be between -1 and 1. So you might want to go -1, 1, -1 to 1 is fine. And let's tell it to graph it. And you might remember this from your Calc 2 days. Okay. If you might remember when you had cosine n theta, when n was even, you have twice that many petals. If it was odd, you had exactly that many petals. So the graph, if I squared it up, the graph has a little petal there, and then you got another one here, and another one here, and another one here. I want to find out the area of that. Now, just like we did in our homework last night, we learned that if you did the double integral of r dA, where you made your integrand just be 1, that gave you the area of region R. Because if you go length times width times height, and your height's 1, you're really just getting length times width, which is your area. Okay? We did that in our homework last night. So what I want to do is I want to integrate over this region of r dr d theta. The question is, what does r range from? What does theta range from? Now what I'd like to do is I'm just going to get the top half. I'm going to get the top half and then just double it. You with me? So I'm just going to find out the area of this, the half the petal, and then just double it. And that'll give me the area of the one petal. Let's take an arbitrary. Now it's almost easier than when you did Calc 2. Because if we take an arbitrary theta, look at that spoke. That's an arbitrary theta in that region, an arbitrary spoke coming out. What is r ranging from? Well, here r is 0, and when I go along that spoke, what's the biggest r I can get? I'm on the petal, aren't I? And on the petal, r is cosine 2 theta. Now we have to see what theta ranges from. It ranges from here, theta is 0. And what does it look like my theta is here? Pi? Pi over 2? Let's look on the calculator. Okay? Let's go on the calculator. I'm going to go to trace. Trace is option F3. Okay. I wish they showed you the screen a little bit. There you go. I'm going to use my little cursor to the right so you can see it. Let's move along. I'm going to go till I get to the inside of that petal. What does it give me? Theta is what? About point what? 0.78 it looks like. Okay, 0.78. All right, now, so I can see the angle's around 0.78. Now I'm going to go to the home screen. Some of you told me pi. Pi's not going to cut it. If I pi on this calculator to get a decimal, you hit the green diamond and then equals. Pi's 3.14. Some of you told me pi over 2. Pi over 2, people. Did I do pi over 2? Oh, no, I didn't do pi over 2. Pi, I'm having problems hitting buttons today. Pi divided by 2, and if I go, give me a decimal, is 1.57. It was 0.78. How can you get that exact? Now, it's going to be pi over 4, and you can try pi over 4 and see that it's exactly that. Let's talk about how can I find out what that theta is. When I've closed the loop, okay, when I've closed the loop, when I'm at the origin, theta could be anything, but to be right on the origin in polar coordinates, what does r have to be? Aha! R has to be 0. All right, now let's look at the graph. Let's look at the graph of R equals cosine 2 theta in rectangular form. Okay? This is going to be my R, this is my theta. You know, just your regular graph of R equals cosine 2 theta. This right here, can anybody remember, what's your period? When it's cosine b theta, what's your period? 2 pi over b, right? Do you remember that? If you had y equals cosine b theta, your period for that is 2 pi over b. That's the width of one complete cycle. So if you have cosine 2 theta, it's going to be 2 pi, your period is going to be 2 pi over 2, which is pi. So that means this graph is going to go through one complete cycle just from 0 to pi. So you have your midpoints and your quarter points. So it starts up at 1, goes to 0, goes to -1, goes to 0, up to 1. This is the graph of like y equals or r equals cosine 2 theta. Notice when theta is 0, r is 1. When theta is 0 degrees, your distance 1 unit from the origin when you're looking at a polar graph. When the very first angle that gives me an r equal to 0 is a theta of what? Pi over 4. That stinking angle's pi over 4. So our limits of integration are going to go from 0 to pi over 4. Okay? We're not going to go through and do this, but I can tell you when you do this integration, you're going to get an answer of pi over 8. I can guarantee you, as you do your integration, blah, 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 you're going to get to a point where you're going to have an integral with a cosine squared of 2 theta in there. That's going to show up in your integration. How do you handle that? You're going to make a substitution that cosine squared theta is 1 plus cosine 2 theta over 2. So if you have cosine squared 2 theta, if you have theta here, it becomes 2 theta. If you have 2 theta here, it becomes 4 theta. Just double the angle. This is the substitution you will do in doing that integral. And I suggest before you do the homework, do this integral. And see, if you don't get pi over 8, come and see me and I'll look at your work. Okay, let's look at this one. Find the volume of the solid that lies under the paraboloid z equals x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared equals 2x. People, we did this 2 minutes ago. A few minutes ago, this graph right here, we figured out was r squared equals 2r cosine theta. We divide it through by r's. We put it in our calculator, and we got that it was a circle that went all the way to 2. It had a max of 2. Its center was at 1, 0. We already did that, so I don't have to do it again. All right, now what's happening here is, this is my rooftop, okay? We want to find the volume of a solid that lies under that paraboloid. Well, what does that paraboloid look like in two-dimensional space? Most of you are good with the paraboloid z equals x squared plus y squared. It looks something like this, right? That's your rooftop. Now my base on the xy plane is this little cylinder. We just figured out a few minutes ago, what does that cylinder look like? Notice, it's a circle hugging the x-axis, right? And it goes all the way to 2. So if I want to draw that in the xy plane, it's going to be doing this. That's my surface. And I'm going to put little perpendiculars up here, and that's my rooftop, and you can sort of see. This is your basis, and then that's your rooftop. All we have to know is the roof is above us, and that's my region. And as we did in our homework last night, your volume is going to be your double integral of your height, your rooftop, which is x squared plus y squared. And we did dA before, but you're going to go r dr d theta. And you just have to figure out what r is ranging from in that region. Well, what is r ranging from? Pick an arbitrary spoke in the region. What's r ranging from? 0? What's r here? 2 cosine theta. And what does my theta range from? If you want to make this one be pi over 2, that would be theta equals pi over 2. This would be theta equals 0. If we continue backwards, this would be theta equals negative pi over 2. Okay, very good. Okay, and if you notice, if you put in pi over 2 here, cosine pi over 2 is 0. Yeah, at pi over 2 I'm at 0, and at minus pi over 2. Now notice, changing this to polars though, x squared plus y squared is r squared. So I have r squared times r dr d theta. I'm not going to bore you to tears, but I promise you, in this integral, guess what? You're going to end up with a cosine to the 4th theta in doing this integration. It happens over and over and over and over again. How are you going to look at that integration with you're going to have a cosine to the 4th theta d theta. What are you going to do? You're going to say, oh, Miss Strocko, that's a cosine squared squared. And you're going to replace cosine squared with 1 plus cosine 2 theta over 2. But unfortunately, you've got to square it. And when you square it, you're going to have a cosine squared 2 theta, which you're going to have to do again, like we talked about. The answer for this, by the way, is 3 pi over 2. Okay? All right, let's do this one. Or at least just set them up. We're going to set them up from now on and not do them. Use a double integral to find the area of the region enclosed by the curve r equals 4 plus 3 cosine theta. If you don't know what that looks like, you really do need to look to see what it looks like. So let's just pop it into the calculator so we can see what he looks like. Popping him in, I hit y equals. All right, I'm going to come up here, bring it down, hit clear. My region is 4 plus 3 cosine theta. Hit enter. You need an appropriate window to be able to get the whole thing. 0 to 2 pi usually is very good for polars, but what should I make my x's range from? What's the most my r could be? If you're going 4 plus 3 cosine theta, the most my r could be is 7. So we're going to go from negative 7 to positive 7 for x, because that's the furthest you are from the origin, negative 7 to 7. And if I look at my graph, I'm going to copy it right here. Okay, you remember doing these. It looks something like this, and it comes around like that. Okay, and this is the graph r equals 4 plus 3 cosine theta. Okay. If I want to get the area, why don't we just get the area of the top half and then double it? All right? So I'm going to double it. And remember, if we go the integral over the region 1 times dA, it will give us the area. So we're going to go 2 times the double integral of r dr d theta. What is r ranging from? Take an arbitrary spoke in the region, arbitrary spoke, any theta equals whatever. What does if you move along that spoke, what's r ranging from? 0 to 4 plus cosine 3 cosine theta. And then remember I doubled it because I'm just going to find the area of the top half because they're equal to each other. Here I have theta equals 0. This is theta equals pi over 2. This is theta equals pi. You also could have gone from 0 all the way to 2 pi if you wanted to get the whole area. You with me? But I'm thinking that might be a little bit easier. Okay. I have the answer posted on the sheet. The answer turns out to be 32 root 3 times pi, but we don't have time to do all of these. You get the idea. This one, when I look at it, it turns out to be 41 pi over 2. I apologize. 41 pi over 2 is what it is, but it's a very easy integral to do. But you know what? It has a cosine squared in it. They all do. They all end up, it happens a lot. Use polar coordinates to find the volume inside this sphere and outside this cylinder. Probably sketching it is the hardest thing to do. This is a sphere of radius what? 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Inside the sphere, so here's my sphere, and you realize I'm going to make this light because it's below. 1, 2, 3, 4. And you also have the part coming around like this. And you can see it back there. Not bad. Okay, that's my sphere. Now we want it to be inside the sphere, but outside the cylinder. What's the cylinder x squared plus y squared equal 4 look like? It has a radius of 2. And the cylinder, you have perpendiculars going up, right? And perpendiculars going down. So can you see what you're doing? This is the base that I'm integrating over, because that's a hole. I'm just taking the part of the sphere. You think of this, you're taking the thing that goes down the middle of the sphere. You put, you're cutting through it. This is void here, and we're just taking the part of the sphere that's below and above. Now the problem is beautifully symmetric, so why don't we just find the volume that's above this region, and then we can double it. So let's find the volume above. And by the way, that region's called a what? An annulus. It's called an annulus. It would be nice to know what you call these. Okay, now, does everybody see what my in the xy plane, what that looks like? Drawing my region in the xy plane, the inner circle is a circle of radius 2, and the outer circle is a circle of radius 4. And we're talking about the region that we're integrating is right there, because the cylinder, we have to be outside that cylinder. What's our rooftop? What's the rooftop? What's the z equal that we're integrating? What's our rooftop? How are we going to do that? Well, our rooftop is the top of the sphere, right? This equation gives us the top of the sphere, but we have to solve for z because it has to be height. So we have z squared equals 16 minus x squared minus y squared, or z is equal to the square root of 16 minus x squared minus y squared. Okay, so for our volume, we're going to integrate our height, which is square root of 16 minus x squared minus y squared dA. But we're going to do it over polars. We could write this as 16 minus quantity, x squared plus y squared. And for dA, put r dr d theta, which is going to give us square root of 16 minus r squared, r dr d theta. What's my r ranging from? Take an arbitrary r. What's r going from? 2 to 4? And what does your theta have to go from? Theta is going to go from 0 all the way around. Theta equals pi over 2. Theta equals pi. Theta equals 3 pi over 2 till I get to theta equals 2 pi. Now this is giving me the part of the sphere that's above the xy plane. So if I want to get the whole part of the sphere that's being cut out by that cylinder, I need to do what to this integral? Double it. Believe it or not, people, this is a very easy integral to do. Because look here, if you let your u be 16 minus r squared, you have a u to the 1/2. There's your du right there. You end up getting this lovely number for the inner integral, so it's not hard at all. It's just that you're getting tired of listening to me, so I'm not going to do it. Okay? A couple more that we just want to set up. Yeah, this is important. Let's set this up. Use polar coordinates, we're going to say, to set up the integral that's going to do it. The cone, let's just draw this. I think drawing it's more important than anything. We have a cone, z equals square root of x squared plus y squared. Here's the cone. Okay, there's my cone. We want to use polar coordinates to find the volume above this cone, but below the sphere. X squared plus y squared plus z squared equals 1 is a sphere of radius 1. 1, 1, 1. So we can go like this, and down like that. It's good enough. Okay, now we want the part of the area, find the volume above the cone. That's here. This is the region right here that we're trying to find. Okay? Now what makes this one hard is that in terms of finding the I'm trying to find my sheet that has the thing right now. In terms of finding a base, it's a bit hard there for you to find. Let me help you find it. In all the other ones we did, it was very obvious that you had a base right in the xy plane. It's not as it's not as easy to see right here. Let's look right, we have right here. Right here is our base. Can you see that? Because you have to find a base so that from that base you can move, you can draw a line that goes to the top and to the bottom. This is the bottom of your volume, and this is the top of your volume. If I took anything down here, I have to make it be right here where they are. Okay, now what I'm going to do right now is I can see that we've gone about an hour and 20 minutes, and I think that's a little bit of a saturation point. What I'm going to do is on the next video, I'm going to finish this one. And I have two more that I'm going to do. I'm going to finish those next time because I know the next section that we're going to do is real short and not nearly as long and tedious as this one. So let's stop where we are right here, right now. By the way, you're more than welcome to try to play with this, but I'm going to blow this up and we'll do the last few. And what I want you people to do is read over on pages 1039 to 1043. And then I want you to do 1 through 13 the odds, 7 to 21 the odds, and a couple here at the very end where it says change your order, change it into polars. If you want, you can skip those and wait because I'm going to do those examples next time. Nah, I think try them. Okay, try them. All right, and I'll see you next time for these last 3 that I have printed out. See you next time.